I'm really sorry for the interruption. Should I? No. Okay. I can do a voiceover afterwards. Okay, so sorry for the interruption. Anything else? No. Okay. So, okay, so this is the problem. You see that here the problem is of fourth order, so it's the Laplacian applied to the Laplacian. So it's fourth order derivatives. And of course, since it's fourth order, you have to impose two boundary conditions. And this becomes evident once you pass to the weak formulation where your functions now are in H2. So they have two traces at the boundary. And in the Dirichlet case, at least, the clamped case, you have to impose two boundary conditions, meaning that both the function and its gradient at the boundary will be zero. And also here there is a self-adjoint operator with compact resolvent, blah, 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 everything. By the way, everything is positive, so the eigenvalues here are all strictly positive. You see that there is still the minimax, but now the Rayleigh quotient is different, because of course the operator here is different. And the final classical operator I want to introduce is this problem here, which is called the buckling eigenvalue problem. This is related again with plates, but this time it's plates when they buckle. So we have already heard about buckling of stuff. And when the plate buckles, this is the problem that becomes relevant. Actually, in the physical case, what's important is the first eigenvalue in this problem. But say for mathematical sake, for interest, abstract interest, we're interested in this problem as it is. You see that this is, in some sense, non-standard. I should not say non-standard because these kind of problems have been studied since at least the 50s. And this is called classically an operator pencil because it's not anymore operator equal eigenvalue, operator of u equal lambda u, but here you have two operators, one here and one here. So that's a pencil. You can switch to the weak formulation as well. You have this problem here. The energy space is, again, h to 0, because, of course, the problem is fourth order, again. And what may not be evident at the first glance is that here also there is a self-adjoint operator with compact resolvent, and therefore we have a minimax representation for all the eigenvalues. Okay, so here there is a Rayleigh quotient, but you see the normalization is not anymore in L2, is in H1 in some sense. And this is related with the fact that the operator is more involved. The underlying operator is more involved than the classical Laplacian or B-Laplacian. So these are pretty classical. Say this buckling problem has been studied at least until the 20s. 20s, not 2020, but 1920. So it's very classical. And for this reason, there has been lots of work. And there are some very classical inequalities that were known at least to Zigo, maybe even before. And the most classical start from this inequality here that you see. It's just an integration by parts and then applying Cauchy-Schwarz or Holder, and you get this inequality to the gradient, and playing around with this inequality, you get this chain on inequalities, where you see that here you have the Rayleigh quotient for the Laplacian, this is the Rayleigh quotient for the B-Laplacian, and this is the Rayleigh quotient for the buckling problem. Now you can take the minimax, and you get the corresponding inequalities, actually, for the eigenvalues, for any eigenvalue, actually, in this order here. And this is classical. Now, talking about optimization, the right question is, are these inequality optimal? What can we say about them? Now, this is an extremely, extremely difficult question for one very simple reason, that is that these eigenvalues are related to radically different operators. So how do you compare them? There are some classical results, for instance, that say that if omega is smooth enough, for instance, I think that C2 is enough for this inequality to become strict because of Pohojaev type identities and analytic continuation, for which you know that, for instance, in this case, you cannot superimpose the fact that the function has a zero number derivative at the boundary, because otherwise you have that only the trivial solution is possible. And something similar can be done also for this inequality that becomes strict if I think omega should be at least C4 or C4 alpha. And I mean, this is all that is known, at least to me. And if you ask about optimization or anything a little farther than that, that's completely open and extremely difficult. So one question is, we could relate, though, we could skip the B-Laplacian and relate the Dirichlet Laplacian with the buckling problem, because after all, you see here in the buckling problem, this is sort of a Laplacian, a masked Laplacian, because you have a Laplacian here, Laplacian square here, so it's like Laplacian of something equal lambda Laplacian, lambda, that's that thing. So you may think, well, maybe this relating this to this is a little easier, and let me say it's just a little easier. And in fact, there is this result due to pain that when you want to just compare the two eigenvalues, this is the Dirichlet Laplacian, this is the buckling, you can do a little better, but just for the first buckling. So using this here, you get that the first buckling eigenvalue is greater than the first Dirichlet Laplacian eigenvalue, but actually you can say that it's greater than the second. And this, in view also of Friedlander's inequality relating Dirichlet Laplacian and Neumann Laplacian eigenvalue, sparkled the natural conjecture that this is not just for the first buckling eigenvalue, but for any eigenvalue. So this became a very popular question last year, 2 years ago. There was some sort of a debate about this going on between several authors, but there was a proof that contained a gap and discussion about that. So this conjecture is completely natural, but the proof is out of reach. And I have reasons to think that in general this is not true, but we can discuss about it later if I have enough time. One final classical inequality, which is again due to pain, is related to a different kind of argument. So if you take the Rayleigh equation for the B-Laplacian, naturally you can split it like this. So this is the buckling, and this is the Dirichlet Laplacian, and so you can take the minimax. So if you go for the minimum, just the minimum, you relate the first eigenvalues of each problem in an easy way, because the minimum of a product is always greater than or equal to the product of the minima. If you want higher eigenvalues, it's trickier, because it's not really the minimax of the product is the product of the minimax. You have to be careful, you have to take out a minimum, so you have this strange inequality, which is much more involved. Essentially, it says that in this product, you have to take one, and you consider the minimum, which is the first eigenvalue, and for the other one, you can do the minimax. So you recover lambda k. And here you can choose on which one you want to take the minimum and on which one you want to go for the minimax. Yes, please. No. Okay, yes, this is something I skipped. So this is a classical question and something that gets people confused. So classically, for this operator, for the Dirichlet Laplacian, you have the maximum principle. The maximum principle, I like to say that it's a terrible result, because it's very strong and it forces lots and lots of properties on second order operators. So here, because of the maximum principle, you have that the first eigenvalue is always simple. The first eigenspace consists of eigenfunctions that have a sign, so they are not zero inside. While here, for the B-Laplacian, and in general for any higher order operator, it's the exact opposite. So like here you have explicit examples of eigenvalue, of first eigenvalue of which are not simple. Anytime you have a corner, the function oscillates infinitely many times around the corner because of the clamp. This is in some sense physically clear, because if you consider a square plate and you just support it and you start pushing it, you do not need to think of concrete, just rubber, for instance. You push it in the middle and you will have the corners go up because it's just supported. If it's clamped, of course they will want to go up. But then you have the clamped, they force it to go down and up and down and up and down. So you have infinitely many oscillation. And this is true not just for the B-Laplacian, this is a result by Kozlov, Kondratiev, and Mazia, 1998, I think, where they say that actually for the polyharmonic problem that I will show you in a minute, all the eigenfunctions oscillate infinitely many times around corners. So and simplicity is even out of the picture. Like for this problem here, together with Enea Parini some couple of years ago, we showed an example of a class of domains when you can choose any k natural, and the first eigenfunction, the first eigenvalue will be of multiplicity k. So I mean, this is you can really play along a lot. So yes, but the first eigenvalue will be anyway strictly positive because 0 is not, the kernel is trivial and the operator is positive, so you cannot have negative eigenvalues. So now there are lots of optimization questions that are extremely difficult, so we cannot work in that direction, so we try to work in other direction. Like for instance, what happens if instead of just considering Laplacian and B-Laplacian, I go to Laplacian to the third, to the fourth, and so on. This to me was natural because I was already working with polyharmonics, so it's a natural question, maybe too much theoretical, but anyway. So the problem we are considering, and the one that I was referring to when I told you about the corners, is this one. So here you see this is a generalized pencil. Sorry, not generalized pencil. This is a pencil which is a generalization of the buckling operator. So you have Laplacian to some power equal Laplacian to some other power. So here, why do I put m and m minus t? Well, I could simply write Laplacian to the alpha equal Laplacian to the beta, something like this. And for some example, it will be easier to think of it like that. Of course, beta must be smaller than, strictly smaller than alpha, otherwise you can flip it over. And the idea is that here, the relevant orders are not the two exponents, but are m, which 2m is the maxima, is the degree of the equation, and the difference of the orders, for a reason that will be clearer in the next slide. So this problem, as well as a weak representation, now the energy space is Hm0. Again, I'm always considering Dirichlet boundary conditions because these are simple and yet they present interesting results. If you consider different type of boundary conditions, we will have, we've seen something in this direction. By the way, this is a joint work with Pedro Freitas from Instituto Superior Técnico in Lisbon. And with different boundary conditions, you have a completely different behavior of the operator. Now here, for simplicity, I use what I like to call the physicist notation, where nabla square is the Laplacian. Because, I mean, I don't like it as a mathematician, but I find it very useful in this situation, so I will use it. And of course, here also there is the minimax. And let me say something that is not relevant for my talk, but which is classical and provides some ideas for later on. That is the Weil asymptotics. So all these problems present Weil asymptotics. Pencils are, say, some sort of non-classical, but were considered by Rosenblum in the 70s, at least. And you see that here, in the Weil asymptotic, this is 2 pi k, and omega d is the measure of the unit ball, and measure of omega is classical. And this, when t is equal to 2, is precisely the first term in the Weil asymptotic of the Laplacian. And so you see that here, the order that matters is t, or 2t, which is the difference of the two. And I may be referring to it as the Weil order of the eigenvalues of the problem, because it's the difference of the orders. And so it's, in some sense, it's what the operator is doing, actually. And so you see that here it's important. Of course, the order m is somewhere hidden here, but for the first term, it's what's matter is just t and not m. So now the question is, what can we do in terms of inequalities? How do the eigenvalues of these problems relate to each other? And we discovered an intricate hierarchy between these eigenvalues. And most of them can be recovered, not in a simple way, but not even impossible way, starting from an inequality of this type. So now, since we are not just taking the gradient and the Laplacian, of course, you have to go to something like nabla to the p, which I recall to you, it's either Laplacian to some power or gradient of the Laplacian to some power. Now here you integrate by parts, you take Cauchy parts, and you get this inequality. And the next 3 inequalities that I will show you start just from here. So in particular, the question of how good are these inequalities is essentially all here. And say the goodness, how good this inequality is, depend exclusively on the Cauchy-Schwarz inequality. But now the problem is that we are going to take minimax. So there will be lots of different eigenfunctions involved. And how do they relate to each other? Who knows? So this is very difficult. Now, the first inequality I show you is this one. So here there are lots of m and t's, m plus 1, t plus 1. So what's happening? So in this situation here, I'm keeping beta fixed, but I'm letting alpha grow. Okay, so when beta is fixed and alpha grows, you have that you're going higher in order, also in the so-called Weil order, and so you expect the eigenvalues to grow, and not only that, they grow even after you renormalize. So for renormalization reasons, we divide the eigenvalue, we take the eigenvalue to 1 over its Weil order so that they are all comparable to each other. And once you have done this renormalization, you have that when alpha grows, the eigenvalue grows. And this is based just on an inequality between the respective Rayleigh quotients. You take the minimax and you go. This inequality is not extremely difficult to show, and you do it by induction. And in particular, we get this inequality where when you have m and m, essentially, here beta is m minus m, which is 0. So you have the classical polyharmonic problem. And in particular, when you take polyharmonic eigenvalues of increasing order, you go up. You go up even after renormalizing with respect to their order, to their differential order. This, in particular, we discovered later on, is a generalization of an inequality by Pucci and Serin. It's actually a huge improvement because they were able to estimate this eigenvalue here, say any polyharmonic eigenvalue, in terms of Dirichlet-Laplacian eigenvalues. Dirichlet and Neumann Laplacian eigenvalues, actually. What they used was some sort of enhanced Poincaré inequality, and that's why essentially they recovered just Dirichlet Laplacian eigenvalues. Here we use a completely different technique because we estimate the Rayleigh quotients directly, so we get something better. And yes. So the next question is, what happens if instead of fixing one and letting grow the other, I let them grow together? Well, they grow nevertheless. So here, what happens is that I keep the distance between alpha and beta constant. So let's say that the distance is just a Laplacian or a B-Laplacian, and then I let them grow together. Then they still grow together. Of course, here I do not take the renormalization because if the distance between the two exponent is fixed, the order of the eigenvalues, the differential order of the eigenvalues is always the same, so I do not need a renormalization. And here also the proof is even simpler because this inequality between the Rayleigh quotients is even simpler to prove. And again, you can do it easily by induction. And now comes the monster, in the sense that this inequality is what happens when I fix this one. So I have a finite a number of possibilities for this exponent, and I let it move. So essentially, when I fix this one and beta grows, the eigenvalues go down. In a sense, yes, because you see when S is bigger than T, so this grows. The eigenvalue with respect to S is less than the other one. And in particular, this is interesting in the specific case where here you see you have a polyharmonic eigenvalue, so here you have 0. And here you have M1, meaning that the distance between the two is just a Laplacian. And this is easier, and easier, say, to write, but the proof is the same. And the proof here, the proof is not difficult per se, because it's based on this inequality. The proof is difficult of this inequality. So you see, you start from this, you rearrange the terms, you get the right Rayleigh quotients. But written like this, it's difficult to understand what's going on. So once you rewrite the coefficients in order to have some clean exponent for these derivatives, you see that this is some sort of a Gallardo-Nirenberg type inequality, in the sense that you get the estimate of some 2p, no, this is over the p, this is some p order derivative is estimated in terms of a higher order derivative and a lower order derivative. Now, this is not exactly Gallardo-Nirenberg type because you do not have any derivative. You have a specific combination of derivatives. And also the functions u are HM0. So it's not any type of, with any possible boundary datum. But on the other hand, what's nice is that here the constant does not depend on the geometry. And I haven't said it, but in my talk, at least until now, omega is any open set with finite measure, because everything is okay. And I don't recall all the details, but I think that this inequality is true anytime, even if omega is not a finite measure. If it's measurable, it's okay. And the coefficient here is 1. It could be better, it could be improved, probably. But in general, 1 is okay, and it does not depend on the geometry, it does not depend on corners, nothing. Okay, so this is very nice. So you pay and you get dot des, as the Romans used to say. And this is very difficult to show. I mean, the proof is just a page and a half long, but it's an induction on the 3 indices, so it's very involved, and you have to be careful not to get mixed with the indices. But I think it is nice. So the final inequality that I showed you, that was the inequality where you just split the Rayleigh quotient, is even easier because here you take this Rayleigh quotient and you split it in products. This is just one possible form that you get. You can choose to factorize it in a different manner, and you still get it anyway. This is the proof is just that. Even in our preprint, it's just like that. You split the product and you take the minimax. That's it. So this was in this paper by Payne, I think 56. He already discussed the optimality of this inequality for the specific case of the Laplacian and the Laplacian. And the question is extremely difficult. I think that Cavol has worked on this some 10 years, 20 years ago, probably. I recall having a discussion with him. I don't recall what we said to each other, because essentially this problem is extremely difficult. This is a very easy inequality to get, but how off it is, it's even impossible to imagine. I have not a clear picture of what happens. Now I showed you lots and lots of inequalities and no optimization so far. So what do we do with this? We try to do something anyway. So the idea is that, of course, if I fix this and I let this move, I have just a finite number of choices. But if I let them grow together or separately to infinity, I can ask what happens. I mean, after all, it's an increasing sequence, which always has a limit. So what's the limit? And the answer is, in general, who knows? I mean, actually, you can show that the limit has to be infinity because it's essentially an exponential. So it has to go to infinity, but how? And of course, in general, since you are comparing eigenvalues of completely different operators, there are no standard techniques. We tried something, didn't work. So when you do not know what to do, you go where you can do explicit computations. That is on the ball. So on the ball, there is a classical way of writing the eigenfunctions and therefore the eigenvalues, of course, using Bessel functions. And let me recall that I will denote by sk any spherical harmonic function of order k. For those of you who do not know what is a spherical harmonic, this is, you can think of it as the projection on the sphere of a polynomial over a harmonic polynomial of degree k. But actually, I will use them because these are the eigenfunctions of the Laplace-Beltrami operator, that is the Laplacian, on the sphere. And by J tilde, I will represent the ultraspherical Bessel function. Bessel function is essentially the radial part of an eigenfunction of the Laplacian. And in my case, I need the ultraspherical one because I'm working in any dimension D. And this is the right renormalization. So this is classical in theory, but in practice is extremely difficult. So you can rewrite your operator, your equation like this. So you factorize one Laplacian out, and you're left with something like a Helmholtz equation, which, by the way, I didn't write it here, but you can still factorize it using complex roots of the eigenvalue, which is positive. And then your eigenfunction will look like this. You will have a spherical part, which is a spherical harmonic of degree k, and a radial part, which is a combination. So this combination is given by polyharmonic polynomials, which comes from here. And here you have the Bessel function coming from here. Now, 2 comments. First comment, you see that here you have gamma, which is a complex root of the eigenvalue. So you're now working with the Bessel functions with a complex argument. Good luck with that. And second comment, what is classical here is to say, for instance, for the Laplacian, which is the easy case. Well, my eigenfunction should look like this. It's easy to show that all of these things are eigenfunctions, and then you prove a posteriori that this forms a complete system. Now, in theory, this is possible also here, but I wouldn't ask to do something like that to anybody, because it's really not the right way to do, and you are forced to do lots of computations. The good way to do is to go is what is essentially very well known in the operator theory community, that is, well, this problem here is rotation invariant, meaning that since when you rotate, the Laplacian doesn't feel the rotation. It keeps working the same way. And in particular, you have that if you take as a second operator the Laplace-Beltrami operator, they commute. So now you restrict to a finite dimensional space, like an eigenspace, and there are operators, commuting operators on a finite dimensional space, meaning they are commuting symmetric matrices on a finite dimensional space. And therefore, they are simultaneously diagonalizable. And since they are simultaneously diagonalizable, you get a priori that all eigenfunctions must look like this. So you do not have to prove that this is a complete system. You have it for free. And this is the easy part of the argument now. Because now we want to compute, we are still left with these coefficients to compute, and we do not know what the eigenvalue is. So we have to do something. Now, we haven't imposed the boundary conditions yet, and once you impose the boundary condition, you have some conditions on the coefficients, which means you have a linear system, and since you want a homogeneous linear system, you want it to have a non-trivial solution, so you have to impose the determinant of the associated matrix to be 0. So if the matrix is A, you set the determinant to be 0, and this becomes an equation for the eigenvalue. Because now I do not really care about the coefficients here, because it's too many coefficients, and I'm not really interested in the actual form of the eigenspaces. I don't care about that. I care about the eigenvalue. So I just get an equation for the eigenvalue, which is actually involved because the matrix is involved. So when t is equal to 1, meaning that here the distance is just a Laplacian, you get all these contributions from the so-called polyharmonic polynomials, and the last row here you have just the last column, which is related with the Helmholtz part of the operator, and so you have Bessel functions. And the rows here, this row here is associated with the condition the function is 0 at the boundary. Here is the condition the normal derivative is 0 at the boundary. This is the second normal derivative 0 at the boundary, and so on and so forth. So you want to compute the determinant of this. What do? What I tell to my students, you tend to avoid using the Laplace decomposition. You try to go for the Gaussian reduction. And actually you can do some Gaussian reduction. So here is the general form for the first, how many are they? Some rows will be, some columns would be polyharmonic polynomials, and the other ones will be Bessel functions. And actually, once you have done this Gaussian reduction, which is not at all trivial, you get essentially a block matrix. The two blocks on the diagonal are squares. You can compute determinants, and the other two, the other two is 0, so it's enough. And you have this B matrix, which is the higher block, which is just something that depends on K and T in this case. And this other block is a block, a complicated block involving Bessel functions. That you have to expect it. So once you have done this, the determinant of the matrix A is just some -1 to some power, the determinant of this block B, and the determinant of this block L. The determinant of this block B, surprisingly, does not depend on K. This is a surprise. The matrix itself depends on K, but the determinant does not. And this determinant L is the one that involves the eigenvalue, and therefore the eigenvalues are all the solutions to this thing here. Now, this is an involved matrix with Bessel functions, with complex arguments, so it's something that you really try to push it away, but if you have to do computations, you cannot push it too far away. And the nice thing is that if t is equal to 1, so in the case where the distance here is just a Laplacian, you really see a Laplacian, because all the solutions here are zeros of Bessel functions, okay? So not all the zeros of all possible Bessel functions involved, but they're all zeros of Bessel functions. Now, this ends the computational part for us, but there are some questions. So, because if t is equal to 1, you just have Bessel function. This is a 1-by-1 matrix, so its determinant is straightforward, and it's a Bessel function. And zeros of Bessel functions are extremely well known nowadays, so you know interlacing properties, asymptotic properties, lots of properties. But when t is different from 1, there not so much is known. When t is equal to 2, meaning that there is a B Laplacian involved, something can still be said using Bessel functions, because it's the relation is not straightforward, but almost straightforward. But already when t is equal to 3, you cannot avoid complex arguments, and nothing is known. So there are some open questions that we would like to answer. I mean, not ourselves, we would like to ask some specialists in special functions, but they are very interesting. So, of course, how many solutions are for each k? So if you take the Bessel functions jk, you have infinitely many zeros. What happens here? Who knows? We expect that for each k there are infinitely many zeros, but it's extremely difficult to show. So the interlacing also, this is related to Bourget hypothesis for Bessel functions. And finally, the asymptotics of the zeros. Because if you have the asymptotics of the zeros here, meaning you have asymptotics for the eigenvalues, maybe you can understand better how the limit behaves. And in fact, say, if we now come back to the eigenvalues on the ball, now in general, for general MNT, there is this expression with this matrix with Bessel functions, so who knows. But thanks to the inequalities we derived at the beginning, we can now bound this eigenvalue, the first eigenvalue, from above and below with zeros of Bessel functions, some products, some powers of zero Bessel functions. And for these quantities here, these small j's are zeros of Bessel functions, we know the asymptotics. So we can take the asymptotics, and if you fix t, so the distance here is fixed, and you send them both together at plus infinity, the asymptotics is clear. It's like m to the 2t, full stop. I mean, there are lower order terms, which are a little more difficult to compute, but still. So now the other interesting question is, what happens if this is fixed and this goes to plus infinity? Well, we can still use this inequality, this chain of inequalities, but the asymptotics here are not as clear. So here you have to renormalize them, because otherwise they really explode, but still you get the general behavior. They behave like m, but the constant is not so clear. Because the problem is that this behaves similarly, but not exactly the same, so the behavior is not ensured. And so we said, okay, but this is an interesting case, because, by the way, if h is equal to 0, you have the classical polyharmonic eigenvalues, and we would like to say something more. And so we worked a little more, and we found better bounds for the eigenvalues of the first eigenvalue, sorry, of the purely polyharmonic case. So the upper bound is given in, we recovered it using specific test functions. And the lower bound, we got it using a very strange auxiliary problem with a non-finite weight, a non-L infinity weight, which was very strange. And you see that there is the appearance of Euler gamma functions for which the asymptotics are known. And you see that the asymptotics of the upper and lower bound are the same apart from this coefficient here, which is just dependent on the dimension. And but the rest, all the rest is the same. So you can take the asymptotics, in particular once you scale with the order, and we are able to get up to the second order. That is a logarithmic term. And for general H, the estimate is not as fine as we would like to. So we get the first term, and the second term we can say it's of logarithmic type. Now, you may say, okay, very interesting. What's the use of it? I may say that I did it just because I like it, but actually we discovered that this is an interesting problem in applications, because there is a paper by Ervedosa dated 2008, 2009, where he's interested in some control problem. Please don't ask me about control problems because I don't know anything about them, but he arrives to consider something like this. He works in a one-dimensional case, but this is the dimension one is included here, and he considered this quantity, specifically this quantity in dimension one, and he would like to have that this quantity is not necessarily bounded at infinity, but has a he wants this specific quantity with the renormalization to be bounded at infinity, and the answer is no. Sorry, Ervedosa, this does not hold. Now I don't remember the implication for his problem, but I think that probably there exists no control. Please don't take my word because I don't remember the paper by Ervedosa. It was like 35 pages long, and it's something I do not work on, so I may have not understood correctly his work. So I don't know if I still have a lot of time. How many minutes do I have? Okay, well, it's okay to conclude. So now, if you think of asymptotics, here there is the ball, and this is the only case. So you may think, okay, for a general domain, maybe the behavior is similar to that of the Weyl asymptotic, where the dependency is just upon the measure of omega. And the answer is, again, no. Because we have a counterexample with the rectangle, so be advised that with the polyharmonic operators, you cannot separate variables because the derivatives interlace. But here we can use a separation of argument of variables argument, and you take a rectangle or hyperrectangle. So here is rho is half the minimal length. And we can get the asymptotics, in the same asymptotics in the case of the rectangle. And you see there is no measure of the rectangle, but there is the half minimal length. So what is this rho? Actually, rho is the in radius of this rectangle. And you see that essentially you can take the rectangle and enlarge it in whatever dimension, and the asymptotics do not change. And this led us to propose this conjecture where for any omega of finite measure, that is when the eigenvalues are well defined, the first term of the asymptotics should be like this, so 2m over e times rho. And why is that? It's not just because it happens on the ball and on the rectangle, but it is because essentially when m goes to plus infinity, your energy space is hm, and if m is high enough, is big enough, your eigenfunctions will be at least ck. So you fix k, and you get an m, for which all the eigenfunctions will be ck. So when you go to plus infinity, your eigenfunctions become smoother and smoother, and they have to be zero at the boundary with all their derivatives. So in a sense, they should perceive which is the minimal dimension of the domain. And the minimal dimension is just the in radius. So we propose this conjecture, which we have no idea whatsoever how to attack it in general, but it seems plausible. It may be false. If anybody of you prove it false, please email me. I will be very interested to see a counterexample. And so I would like to conclude with what happens for other domains and higher eigenvalues. Well, in this case, we have some estimates in the case of the ball for higher eigenvalues, which are not as fine as we would like to. And in any case, for a general domain and general eigenvalue, you can use a trick by Polia. That is, you take a domain and you get k balls, k equal balls inside of it, so you get an estimate from above, and you enclose omega into k equal balls, and so you get an estimate from below. And that tells you that essentially the behavior is the same, apart from the constant, which of course is not known. And I prepared some other slides that I do not have the time to go through, and probably they're not so interesting. So I will stop here, and I thank you for your attention. So, okay, I skipped this because this is a very dense thing. So let me go back to the beginning. So for the Dirichlet Laplacian, there is the Faber-Krahn inequality, meaning that lambda 1 is minimized by the ball. For this, the B Laplacian, it's extremely difficult. There are some results. I did also some results in this direction for which the ball should be the minimizer. This has been proved in 2 and 3 dimensions using an argument due to Talenti. The proof is not good in the sense that it's the same proof, it's fine, but those arguments are not well adapted to the problem. And we expect that the arguments needed to prove it in full dimension is different. I've been working and keep working on this problem because it's very interesting to me. In this case, there have been some discussion about this. I think this problem here is intimately linked to this one because there are lots of relationship between the two. And actually the same order of ideas suggests that some sort of the same inequality, meaning that the first eigenvalue of this problem for any m and for any t should be minimized with volume constraint by the ball. Now, how to prove it? There are some ideas, but they are still very, 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 very preliminary. It's not clear what happens also because here in full general, like, okay, for instance, already here for the B Laplacian, the pure B Laplacian, no, not this one, already here it's complicated because, I mean, it seems not that much, but the fact that you must have second order derivative, it's a very huge impediment for the type of arguments that are available, probably even more than the lack of maximum principle. Because essentially, say, when you work with a problem like this, the fact that you just have L2 or LP derivative, it's okay, it's telling you that the function is smooth, but not really. It can be very, very rough. Here, you have second derivatives. And this seems like a small gap, but it's already huge. My idea is that once we understood how to prove Faber-Krahn here, it should be easy to prove Faber-Krahn for all the other ones, but it may be completely wrong. Also, by the way, one other issue here is that there is the capacity, which is very, very hidden inside it, that it's changing for all of them. Like here, the critical dimension is 2. So you don't really see the difference. But here, the critical dimension is 4. And that's why the proof of Ash, Bobenguri, and Nadirashvili of the Faber-Krahn in dimension 2 and 3 works only in 2 and 3. Because there is, for sure, a switch when you pass to higher dimension. And this, you can see it also for some inequalities for the Neumann B Laplacian, where in dimension 2 and 3, something happens. In dimension 4 or higher, something completely different happens. But this is an interesting question. It seems like nobody's working on it because it's too hard, but there are people working on it. I know, and the answer is not really. So if I understand correctly, here, for instance, you have the Alexandrov-Serrin moving plane arguments, stuff like that work. And it works very nicely, very smoothly. Here, there are some results by Dalmasou for moving planes. And the problem is that there you need the maximum principle. You need something to be positive. And it's very subtle in the proof to the point that I wrote to Dalmasou because I couldn't find where he used the positivity. So I hope this was the question. Yeah. I mean, if you're thinking about symmetrization like Schwarz, rearrangement, stuff like that, the issue is not the maximum principle. The issue is the regularity. It's really the regularity. Because like the Fabre-Kran here usually is proved through rearranging the function. So you rearrange the function, your arranged function is still H1, so everything works. Of course, you need some lower bound, because otherwise you can go to minus infinity or plus infinity. I mean, you cannot go to both together. You have to have a bound from one side. And if you do not have the bound, whatever. I mean, it could be not even not LP. Here, for higher order operators, it seems like, yes, positivity is an issue, but the bigger issue is the fact that when you rearrange, you lose lots and lots of regularity, so you have to rearrange in a different way, and even so it's not clear what would be the right way or the right thing to rearrange. Yeah.
You were saying that if you have the first eigenvalue. We did that for some classes of operators.
Okay, so for the Bilaplacian, there is this result by Marcone Pereira, where he shows that for the Bilaplacian there is generic simplicity. My expectation is that the generic simplicity should work also for in this case here, in the most general problem, in this case here, it should work, but the arguments are really involved because essentially you pass through some Pokhozaev type inequality, but you could do it also through Hadamard, the shape derivatives of the eigenvalues, which are extremely difficult to compute and then extremely difficult to employ. But I mean, the general setup suggests that you should have generic simplicity here. However, this is a mistake that I've seen in many papers. Be advised that whenever you use perturbation type arguments, you cannot use generic simplicity, because generic simplicity means in whichever point you are, you can move just a little and you have simplicity. But if you're doing perturbations, you do not know where you're moving. And but yes. So let me say this: in some sense, the Laplacian is the black sheep of the family, because you have the maximum principle. So it's too nice. It's too nice of a problem, and you have so many properties that you do not really realize when you go to higher order that you cannot use that, because that comes from a long distance from the maximum principle.